Hey guys, welcome back to our next lesson. We recently looked at a problem where adding up successive outputs of a function and treating those as their own outputs in a new function was desirable. And so our focus as we dive into our next unit here is going to be on finding sums. Today's focus is we're going to learn some tricks for finding certain sums. And we're going to focus on very specific patterns that we've learned today. And that would be arithmetic and geometric sequences. First of all, our mindset message is, I think this goes along with what we're doing today, because I think a lot of the patterns we're going to look at and a lot of the methods that we're going to talk about for finding some of these sums are really cool and they're really beautiful, and some people put a lot of hard work into developing these things. Our main learning goal for today is to find sums of finite arithmetic and geometric sequences. And when I say finite, I just mean we know an arithmetic or geometric sequence could go forever, right? So we're thinking if we had a chunk, right, a section of one of those sequences, if we want to add all the terms up in a simpler way than just adding them up directly, how could we do that? Prior knowledge today would clearly be remembering an arithmetic and geometric sequence and what they are. So remember, arithmetic sequences have a common difference, right? They add the same thing again and again and again. And they very directly correlate with a linear function, outputs of a linear function. For example, if I start with 2 and I add 3, I get this sequence. Now, a geometric sequence, instead of having a common difference, has a common ratio, right? If you take the ratio of any two successive terms, it's going to stay constant. And that really goes with exponential functions. So these can be seen as the outputs of an exponential function. So this one also starts with 2, and it also involves 3, but its common ratio, it's multiplying by 3 to get each new term, right? And that's the difference between those two things. So why don't we go ahead and dive in and take a look at how we can find sums of these two different kinds of sequences. We're going to start with a warm-up example here real quick, something we've done in the past. Go ahead and try to find the missing terms of the sequence. You'll notice this is the same starting and ending number here. However, treat it as arithmetic here and geometric here. Go ahead and pause right now and work that through yourself. So here are the answers for this. Now, a lot of approaches are possible here. You can kind of just work it through in your head and just try to figure out, okay, well, what do I need to get here? This one means I have to add the same thing. This one means I have to multiply the same thing, and sort of kind of get there, right? But a more methodical approach we've learned, don't forget, in this case, there are 3. In this case, we're adding, we'll usually call it D, right? So you can think 9 plus 3Ds will end at 72, right? And that turns into solving a linear equation, essentially. And then you work it out, and you're going to get that D equals 21, and then you can proceed from there. Similarly, we typically call this, if I'm multiplying common ratio, we usually call it R. So what we have in this case is 9 times R 3 times equals 72. And that means 9R cubed equals 72, which again you could solve. So D equals 21 here, and you can solve this and you get R equals 2, and then you just proceed from there multiplying by 2, right? So those are some ways we've worked with these in the past, but now let's dive into figuring out how could we find sums of some sequences like these. So let's start by honing in on arithmetic sequences and looking at sums of those. Now, one of the most familiar arithmetic sequences that we've seen, and we've seen this early in this course, it's been a while, is looking at simply the sum of the counting numbers. So 1, 2, 3, 4, etc. And this says find an easy way to add the numbers from 1 to 100, right? The counting numbers. Now that's clearly arithmetic sequence, because we start with 1 and we're adding 1 each time to get to the next term, right? So the common difference is 1 technically. And you can think back to some of the things we learned earlier in the course, but I'm also going to introduce you to various ways we could look at this right now. But go ahead and just try to think about a simple way you could figure this out. Now that you've done a little bit of thinking there, one strategy we often use, in fact we use this in all over the place in math, is if we have a kind of difficult problem, what if we solve a simpler version of the problem and then try to learn from that first? So let's actually first consider just the sum 1 plus 2 plus 3 plus 4 plus 5. So one way we could think about this is what I would call averaging, or thinking about the averages of all the numbers that are in the sequence. You also might think of this as being called redistribution. Now, I like looking at this example because if you think about redistributing the higher numbers onto the lower numbers to make them all equal, that's kind of what we mean by averaging, right? If you notice, if we take a number off of 4 and bring it here, then this drops to 3 and this comes up to 3. And if we take 2 off of here and put them onto here, they also both become 3. In fact, you can see the average of all these numbers happens to be 3. And if it's an arithmetic sequence, something special is true about it, and that's that the number in the very center is the average. And so that's a tricky way we can do this, because you can agree with me that if I just took some numbers off of this over here, and then it would be the same as having 3 copies of 5. So it seems to be true that this is equal to 3 times 5, which is 15, which of course you could go ahead and confirm that by adding them up. Now we could apply that same thing to our more difficult problem here, and we could say, okay, well, what number's in the middle? This one's a little bit trickier because this has an odd number of terms, and so there is one single number in the middle. This has an even number of terms. So the question is, wait a minute, is it 50 or is it 51? Well, it's actually going to be not part of the sequence itself. The average happens to be the very middle of that, which is 50.5. So if we redistributed all of these numbers here, you'd essentially have 100 copies of 50.5. Well, if 50.5 is my average and we're multiplying it by 100 here, then we get 5,050. And again, you could go back if you so choose to confirm that that sum really happens to be 5,050. Let's look at another method here. Well, another way we could use, and this way may look familiar to you, is we can think about it visually, and we're going to use the idea of stairs. So we can think of this arithmetic sequence, right, as stairs that are sequentially increasing in height, right? And in our case, they're increasing by 1 each time, but let's say your common difference was 2. You would just have each one going up by 2 each time, but it'd still have a common difference, and this general way of thinking about it and this method would actually work with it. Now, the cool thing is there an easy way to count how many squares there are here without just going 1, 2, 3, 4, 5, etc.? And it turns out one really nice way of doing this is essentially doubling it and creating a rectangle out of it. Now, I'm actually going to scooch up here, and I've created one here out of colored blocks. And the cool thing here is I've doubled it to help you see that, notice this height is 5. But if I were to put this together, and in fact the width is 5 too, I doubled it and put it together to a rectangle, but now this last stair here is added on. So this is actually now a 5 by 6 rectangle, or 6 by 5, however you want to think about it. So if we doubled that, the actual staircase I started with is just half. But isn't it easier to calculate or figure out how many squares there are in the rectangle in one easy calculation, and then divide it by 2? Yeah. So let's do that here. So again, if you imagine the whole rectangle, it's a 6 by 5 rectangle, but there are half of the squares in our staircase that actually are what we want to count. So this calculation can be done by 6 times 5 divided by 2. 6 times 5 divided by 2, well, that's 30 over 2, which is 15, and that agrees with what we got earlier. Now again, let's go and apply this logic. We're not going to draw the full staircase for this one, but apply that logic to our sum. So again, if we have a staircase, let's just say that goes from 1 step all the way to 100 square, or 1 square to 100 squares, right? And again, we double it, stack it, make a rectangle. It's still the case that this single first step stacks on top of there, just like before. And so the dimensions of this thing happen to be now 101 by 100. And we want half of it. So you see how there's a repetition going on here in our calculation. So it seems like our sum here is going to be 100. I guess I'll keep with the right order here. 101 times 100 all over 2. And if we were to actually calculate that, that's going to end up being 5,050, just like we got before. Now let's look at the official method that's kind of named after Gauss, which, to be honest, is actually pretty much the same as this, but doesn't involve the visual. Now we're officially at what we'll call Gauss's method. And I'll be honest with you, we could almost say this is the stair method non-visually, I guess. So what we're going to do is we're going to take this sum and we're going to call it S. And what we're going to do is we're actually going to rewrite S again. Okay? We're going to repeat S, but we're going to write it backwards. 5 plus 4 plus 3 plus 2 plus 1. There's an ingenious thing going on here, because if we actually take this sum and add it to itself, however, it's written backwards now. What we're essentially doing is we're essentially matching the outside terms with the next terms, etc., almost like a little rainbow here. Okay, when we write it backwards, that's kind of what we're doing. Because look at what happens here. 1 plus 5 makes 6, 2 plus 4 makes 6. In fact, all the number pairs, when I write them backwards like this and add them, all line up and make the same sum the entire time. So what we end up here is S plus S gives me 2 S's, if I add these. And then let's just make a shortcut out of this. This becomes 6 plus blah, 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 right? Plus 6 plus 6, 5 times. So really this is 6 times 5. And therefore S equals 6 times 5 over 2, which just so happens to be 30 over 2, which is 15. Again. So this right here really is the same idea as what we just did, but it's a really cool way that we can actually lay it out without actually drawing it out. So let's go back to the very start, the problem we started with, and let's apply Gauss's method. We'll again just call this S, and then repeat himself written backwards, and then follow through. Go ahead and finish that yourself real quick, just to check. So let's check your work. We rewrote the sum backwards, and then we get 2S equals, these pairs all add up to 101. Well, how many pairs of 101s do I have here? I have exactly 100 of them, right? So you have to be able to know how many terms there are in the sequence here to do this. And so we can shorten this by saying, oh, okay, so there's 100 copies of 101 here, and dividing by 2, we still get 50-50 just like I did before. Let's get a little bit more practice now. So go ahead and do these on your own, or attempt to. Use Gauss's method to find the following sums. If you'd really like to try to take a stab at these using one of the other methods we did, that's totally fine as well, actually. But when I show my work, will use Gauss's method. And then there are a few things to make note of here. First of all, this one's a little different because it starts not with 1, right? And you have to end up counting how many pairs there are going to be. I'm just going to shout something out to you. Think carefully here. It's tempting to think that, oh, we have 3 things here, 1, 2, 3, and then 84 things, so 3 plus 84. But don't forget that 0 in the middle there, right? In general, when we're counting, you're usually going to add 1 more than what you think you should have. So actually, 84 plus 3 is 87, and then the 0. So there's actually 88 pairs here. And then this one here is interesting because you're going to be actually adding them up to n, which means you're developing a formula for the sum of counting numbers here. And this one here is a little different because this one is no longer just going up by 1. These are actually the even numbers from 2 up to 50. So when you pair them up, it's not going to just be 50 pairs anymore, right? You might guess it's going to be half of that. So now go ahead and finish these on your own, and we'll just look at the work in a moment. Okay, we're back. You can go ahead and just do a quick check of your answers for these, and if you got them all correct, then you're good, and you can move on. Except, real quick, make special note of this formula. The sum of the first n counting numbers is n plus 1 times n all over 2, or sometimes the n is first, so n times n plus 1 all over 2. Okay? A few comments to make here just in general. You might notice all the ones that started with 1 and were just going up, basically adding the first counting numbers. You might have noticed that it was always the number times 1 more than itself over 2. Every single time we added the counting numbers starting with 1, it did that. Now, once we broke away from starting with 1, like this -3, you'll notice this is 88 times 81. So those aren't the number and the next one anymore. But this process can still work for these other ones. That's why Gauss's method is pretty powerful. And it even works for ones that aren't spaced just one apart, right? In this case, our common difference is 2, and it still worked out. You just need to make sure you're able to count how many pairs there are and work that out. Okay? But there's one very special formula here that you should really make note of, and that is if we want to add up the first n counting numbers like we did here. This concludes our portion of this lesson on arithmetic sequences and finding their sums using those methods. Next, we're going to look at finding sums of geometric sequences.